All right, did you have a chance to look back at your notes? Did you have the glycine structure drawn there? Okay. And so when we compare glycine to propanoic acid, I drew it differently in class, but if we put this lone pair in the plane and this bond in the plane, then that means one bond sticks out, the other bond sticks in. So we'll put the hydrogens here. And then we have the zigzag pattern with the carbons. So how many carbons in glycine? 2? Yeah. And so one hydrogen is going to stick out, the other hydrogen is going to stick in. And this carbon is a carboxylic acid carbon. So what we're going to do is we're going to put the double bond O here, and then we'll put this here, and then have the hydrogen. So we kind of have this zigzag thing here. This oxygen is tetrahedral here, the electron pair geometry. So we did this here. All right, so that's glycine. If we compare it to propanoic acid, comparing it to propanoic acid, it's very similar, except rather than having this structure, what is this structure here called? What is that geometry called? This geometry would be, well, it's a tetrahedral set geometry. What is the molecular geometry? It's not bent. Trigonal. Pyramidal. Yeah, it's because the it is tetrahedral in the sense that we have 4 balloons. You know, it's a tetrahedral arrangement of balloons. 1, 2, 3, 4, something like that. Because these 4 balloons, they're going to adopt a tetrahedral. But when we look at the geometry, the molecular geometry, we don't look at those. We look at the balloons formed by the atoms. And so if we just look at the balloons formed by the atoms, then it's a trigonal pyramidal shaped balloon. So these 3 balloons are sticking down like that. For propanoic acid, though, it's simpler. Propanoic acid is simpler because on the end here, we just have the CH3 group. The CH3 is this group like this, and then we'll put this hydrogen bond here and this bond to the carbon in the plane. And so when we look at this end carbon is both tetrahedral set or electron pair geometry, EPG, and the molecular geometry would also be tetrahedral. And so this is a case where the blue and the green would match up here. Tetrahedral. And then pretty much the same, the rest of the molecules the same. Yeah. What's the geometry on the carbon of this one here? Well, EPG is trigonal planar, and the MG is trigonal planar. They're both the same. This is flat, completely flat. This is not flat here. This is pyramidal shape, and so this is flat in the plane. You know, some people are trying to draw a bond coming out, but I guess you could, but you have to think, you know. It has to be completely flat, and so if you have bonds coming out, you got to make sure that there's bonds going in to compensate for that. Okay. So we try to draw as much of the molecule flat in the page. So this H, this C, this C, this C, this O, and this O, this H are all flat in the page, and others stick in and out. Right, so it's just this. Rather than having a tetrahedral trigonal pyramidal on the left end, we have a tetrahedral on the left end. Nitrogen. This you know, this is going to be basic. This is like ammonia, right? And so this is what we call the mean. This is not. This is just strictly acid. So these amino acids are kind of interesting. They have the weak base on the left end, or it doesn't matter, left, right. Just on one end we have the weak base. On the other end we have the weak acid. Pretty interesting molecule. All right, any questions on this? Were you able to draw it okay? You know, the drawing, I'm very picky about how it's drawn.
Can we have more, one more example?
Yeah, a lot of people, what they like to do is they like to draw like a tetrahedral like this. But to me, this is a trigonal planar arrangement. You see, I got trigonal planar because everything, these three are in the plane with one sticking out. Is that tetrahedral? No. And so I'm kind of particular about this. So watch out how you draw it. Also, some people get the angles wrong. You know, for example, here, they'll throw this out. But what you have to do is you have to, you know, what some people do, this is what, when I was taking, this is important in organic chemistry, especially. When I was taking organic chemistry, there's one person sitting not far from me. That, he had a stack of pens and pencils on the desk. I was thinking, why do you need so many pencils? Then I figured out why he needed so many pencils. He needed so many pencils because he started making these things with pencils like this, you know, to see the shapes and the geometries and that type of stuff. Because in organic chemistry, everybody's required to buy a model kit. So when you practice enough with a model kit, you can just visualize things in your mind, but sometimes it's helps, you know, especially when you're looking at complex reactions, you know, what's happening with positions. Because it's not just drawing it once, but you're drawing it and then doing a reaction, and then that changes things. And so you got to look at how things are oriented. Because it's like, when we look at organics, you know, there are two common organics, cellulose and starch, you know. Do you know cellulose and starch are kind of made up of the same thing, basically? Cellulose and starch are made up of the same thing. We can eat one, but we can't eat the other, and that's just because the 3D arrangement of this is just, in starch it's one way, in cellulose it's the other way. You know, it's just how it's bonded together. But they're composed of glucose, basically. That's all linked together. And so, you know, this 3D shape is so important. And it's so important in biology. That's where the significance of this is. So this is why people are concerned about. And so you want to draw it as accurately as possible, of course. Okay. And so structure is extremely important in chemistry. We haven't really talked enough about it, but we've got to move on here. So let's move on to where we left off last time. I would have divided this up into two slides. You know, the first part is this is the main type of calculation you did. That was the example we did earlier. And then we have specialized applications of the ideal gas law. So let's take a look at that. So the standard is just an algebraic PV equals nRT. If we're given, you know, there's 1, 2, 3, 4, 5. There's 5. One of them we know. Which one should you know already? N changes. R is a constant. So, you know, if it's a constant, it doesn't change, then we should know that. 0.08206. The units are important there for R as well. R is equal to 0.08206 liters times atmosphere per mole Kelvin. So if we're given 3 of the 4, we can figure out the 4th. And so this is your standard problem. And then, you know, and so we'll just say the way we do this is 1, solve for single variable, solve for variable. That's the first half of this slide here, solve for variable. 2, what we can do is we can do specialized applications. Specialized applications of the ideal gas law. The first specialized application is to solve for the molar mass. The molar mass is equal to the grams per mole. The grams per mole. And this is the molar mass of a gas. It has to be of a gas because we're going to be using the ideal gas law. So if we're looking at the molar mass of a liquid or molar mass of a solid, this is not going to work. The reason this works is because we can relate moles. So this is just equal to the grams divided by N. You know, N is the number of moles. And so this is going to just be equal to grams, well, N, what is N equal to? N is equal to PV over RT for gas. And so what we'll do is we'll just divide this by PV over RT. And so what we're going to get is we're going to get the grams times RT over PV. And so grams is just the mass. So this is equal to the mass times RT over PV. You're thinking, why do we do it in one equation? We could just do it in two separate calculations. One, you have the grams. Two, you calculate the number of moles. That will give you grams per mole. And so this is one. But there's a variation of this. And so we have the molar mass is equal to the mass times RT over PV. But there's one other thing. And the one other thing is this. Mass is in grams. What is volume in? Liters. And typically densities of gases are given in grams per liter. And so there's one more variation of this equation. That is M, mass over volume, is density. And so this is equal to the density, the gas, times RT over P. So another way we could get the molar mass of the gas is by knowing its density or measuring its density of the gas. That's molar mass. All right, then we have another application of this, which would be for density. Let's take a look. Where did this one? Another application of this is for density. Density is grams per liter for gas. Density of gas. Grams per liter for the units. That's because gas is a very low density. Normally densities are grams per milliliter. Gas is mostly empty space. We do grams per liter, which is a more convenient measure of that. In other words, this is mass over volume. Well, we know what volume is. Volume is equal to nRT over P. And so what we'll do is substitute that in here. So the density is equal to the mass divided by nRT over P, which gives us the mass times the pressure divided by nRT. Well, we saw this one before, mass over moles. Do you recall seeing that one? What is mass over moles called?
Molar.
The molar mass. And so we end up with this equation. The density is equal to the molar mass times the pressure divided by RT. And so if we could calculate the density of any gas, let's say you want the density of helium. You want the density of helium gas at, let's say, minus 10 degrees Celsius at a pressure of 1 atmosphere. What is the density? Do you have to measure it? No, you don't have to measure it. You can calculate the density of a gas at any temperature and pressure, which is a very convenient thing to do, as long as you know what the gas is. It's more than that. So we did the pressure of the helium-filled balloon. I don't know why they're using this equation here. It's all right. What is the density of helium at 22 degrees C and 744 torr? So let's do that. The units have to cancel out. And so what we'll say is the density is equal to the molar mass times P over RT. Molar mass times P over RT. So we need the molar mass of helium. What is the molar mass of helium? 4.002 molar mass off the periodic table. And we have to write in the units, 4.002 grams per mole. What is P? 744 torr. What is R? R is 0.08206 liters times atmosphere per mole Kelvin. And what is T? T is 22 degrees C. So what we're going to do is, let's convert it to Kelvin. 22 plus 273 is going to give us 295 Kelvin. We got to make sure the units cancel out. So moles will cancel out moles. Kelvin cancels out Kelvin. Atmospheres and torr don't cancel out. And so do you know a conversion factor to convert one to the other? Yeah, I know a conversion to convert torr into atmospheres. So this 1 atmosphere is equivalent to 760 torr. Okay, and that's going to give me atmospheres canceled. That's going to give me the units of grams per liter. Well, grams per liter, that's what I want for density. And so let's go ahead and do the calculation here. Calculation is 4.002 times 744 divided by 760 divided by 0.08206 divided by 295. 0.16. So I got a density of 0.161. How many sig figs are we allowed? Only 3 here. So 744 torr, 0.1618 grams per liter, or 0.162 grams per liter. So that's what they ended up getting, 0.162. Now, the book is, I think, crazy because the book wants you to memorize a lot of different R's. For example, they want you to memorize R with the units of torr. This is 60. R is 62.4 liters times torr. That would be divided by mole Kelvin. Do you want to memorize? How many different R's do you want to memorize? Just one. If we memorize just one R and then just convert the units to match that R, then we're okay. We don't have to memorize multiple R's. And so just keep in mind your book likes to use different R's for different units. I like to use the same R for all problems and then just make sure all the units are converted. All right, there's one more special application here, and that's called the molar volume. And B, so this will be C here. The molar volume. And the molar mass mm. So the molar volume is just going to be the volume per mole. How many liters per mole? Essentially liters per mole. Would be V over N. Molar volume. This is molar volume. Liters per mole. And so what we're going to do is we're just going to rearrange the ideal gas law. So PV equals nRT. So what we're going to do is we're going to divide both sides by V and divide both sides by N. So we end up with this equation. V over N, sorry, I made a mistake. We divide both sides by P. So this is going to give me V over N is equal to V over N is equal to RT over P. That's the molar volume. So we could calculate the molar volume at any temperature and any pressure. It's simple. So for example, how much space does a liter of gas take? Well, a liter of gas takes a liter, but how much space does a mole of gas take? Well, it really takes a lot more than a liter. And so let's take a look at standard temperature and pressure, STP. And so, for example, STP is called standard temperature and pressure. Standard temperature and pressure. The temperature is equal to 0 degrees C. The pressure is equal to 1 bar. This is a reference point, arbitrary reference point. Somebody just chose it. That's what I mean by arbitrary. But I think it's not that useful. Maybe it's useful. And so what is it? And so the molar volume at STP, let's say at STP, is equal to P, 1 bar. Oh shoot, I have to do one more thing. Sorry. I have to do one more R value. But I'm just going to memorize 1 R. So I have 1 bar, P, oops, goes on the bottom, RT. R, what is R? 0.08206 liters times atmosphere per mole Kelvin. T, what's T? 273 Kelvin would be 0 degrees C. What is P? P is 1 bar. 1 bar. And so this conversion I don't necessarily ask that you memorize. But do you know the conversion between atmospheres and bar? 1 atmosphere is equivalent to, well, you don't have to have it memorized. They're almost the same thing. 1 atmosphere is 1.01325 bar. That will be given. All right, so let's calculate this here. So I'm going to take 0.08206 times 273 divided by, oh actually, let's do not divided by, times. I'm going to back up. Let's do times 1.01325. 2.69. This comes out to 22.6. How many sig figs am I allowed? Looks like I artificially cut it off here. Liters per mole. Units should come out liters per mole. So ATM cancels, bar cancels, Kelvin cancels, it leaves us with liters per mole. And so what did they get? 22.7 liters. What is the molar volume of air at 11 degrees C and 1.33 atmospheres? And so let me tell you, this is for any gas. So for any gas at 0 degrees C and 1 bar pressure, the volume is about 23 liters. 23 liters. Is that very useful? No. In some books they compare different things, but what's more useful is not. Do you do your reactions at 0 degrees C, or do you do your reactions at room temperature?
0 degrees C.
When we go into lab, do we work in a 0 degrees C lab or a room temperature lab? So if we're going to do a chemical reaction, do we want to turn up the AC and blast it? Hopefully it gets down to 0 degrees C. No. No, and so let's look at the molar volume at, what's the typical pressure? Typical pressure is about 1 bar or 1 atmosphere. So we're just gonna go molar volume at 25 degrees C and 1 atmosphere. Atmosphere is just this. You know, the bar comes from physics. The atmosphere comes from observations of normal atmospheric pressure. So we're just gonna go with 1 atmosphere, right? And so let's calculate the molar volume. The molar volume is going to be, well, the pressure is 1 atmosphere. Oops. R 0.08206 liters times atmosphere per mole Kelvin. Temperature is going to be 298 Kelvin. The pressure is going to be 1 atmosphere. So atmospheres cancel, Kelvins cancel, and that gives me liters per mole. So let's go ahead and calculate it. 0.08206 times 298. 24.45. 24.45 liters per mole. And so what happens is, if I have a gas at 0 degrees C and about 1 atmosphere, it's about 23 liters. But if I warm it up to room temperature, it's going to expand a little bit because the hot gases expand, and then it's going to go to about 24 liters, 24.5 liters. Do you see that? And so this is just a rough approximation. A mole of gas at 1 atmosphere in room temperature is 25 liters. So a mole of air is about 25 liters. A mole of oxygen is about 25 liters under these conditions. A mole of nitrogen is about 25 liters. A mole of helium is about 25 liters under these conditions. The densities, of course, are going to be different, but the molar volume is going to all be the same. So what is the molar volume of air at 11 degrees C and 1.33 atmosphere? You know, when I was a Chem 4 student, I had to memorize this number.
You took Chem 4.
I took Chem 4, yeah. Chem 4 style. It wasn't called Chem 4 though. Called something else. Yeah. I never used it since, but it's burned into my memory. I can't forget it. Wasting space. So what is the molar volume of air at 11 degrees C and 1.33 atmospheres? That's the question. So in this example, we want the molar volume of air at 11 degrees C and 1.33 atmospheres. So the molar volume is going to equal RT over P. So R 0.08206 liters times atmosphere per mole Kelvin. 1.33 atmospheres is the pressure. The temperature is 11 degrees C, so 11 plus 273 would be 284 Kelvin, divided by the pressure of 1.33 atmospheres. So let's calculate the molar volume of air. Here. 0.08206 times 284 divided by 1.33. 17.52 liters. What happens is two things. One, the temperature. The colder the temperature, the smaller the volume. And two, the higher the pressure, the smaller the volume. So, you know, this is kind of a small volume here. So 17.5 liters. Okay, so what we're going to do now is molar volume is very useful for stoichiometry calculations or using the ideal gas law for stoichiometry calculations. And so what we can do is we can go from volume. So if you know, let's say at 25 degrees C at 1 atmosphere, if you know a mole is 24.45 liters, then you know if you have 24.45 liters of oxygen, how much is it? It's a mole. If you have 24.45 liters of methane, that's a mole of methane. And so we could do stoichiometry with these numbers, with these molar volumes. So let's just take a look at the stoichiometry equation. The stoichiometry equation is like this. Let's say methane, this will be gas stoichiometry. Gas stoichiometry is the next thing we're looking at. We got methane plus 2O2. Both of these are gases. This is going to go to CO2, gas plus H2O liquid, 2H2O liquid. And so what we can do is this. You know, this is 1 mole. Let's say this is 1 mole. This would be 2 moles. How many moles would this be? 1 mole and 2 moles. And then if we know the molar volume, let's fix the temperature. Let's say at 25 degrees C and 1 atmosphere. Then 1 mole is equivalent to 24.45 liters. And then we double that. This is going to be 48.90 liters. And this will generate 24.45 liters. This is not 48.90 liters. Why? That's not 48.90 liters. It's not a gas, it's a liquid. It's a liquid. This only works for gases. So the easy ratio is this. For every liter of methane, I'm going to need 2 liters or twice as much O2, and I'm going to form 1 liter of CO2. Now, if this were a gas, then we're good. If H2O was a gas, then we'd have 48.9, and then we'd have a liter. Because gas is mostly it's not. We're not going to do gas. This is figure 1414. This is gas stoichiometry at STP. What was STP again?
Standard temperature.
Standard temperature and pressure. We're not going to work in an ice box, you know. And so I'm going to skip this. Gas stoichiometry at STP. All right, this is gas stoichiometry, not at STP. Let's take a look at this one here. This is another combustion reaction. This is a combustion of not methane. This is a combustion of butane. So how many liters of CO2 measured at 744 torr and 131 degrees C will be produced by the complete burning of 16.2 grams of gaseous butane, C4H10? The equation is so this is just this is another stoichiometry type problem in which what we're going to do is, okay, in this example we have 2 butanes, 2,4-C4H10 gas plus 13O2 gas yields 8 CO2 gas plus 10 H2O liquid. So what I'm going to do is I'm going to go from grams of butane, C4H10, to moles of butane. From moles of butane, I'm going to go to moles of CO2. From moles of CO2, that's what we call N, right? N for CO2. So I have 2 options here. Go to volume. One option is using the molar volume. The other option is to use V is equal to nRT over P. And so we'll do option 1 and option 2 as far as the setups go. So option 1 is like this. It's just going to be straight dimensional analysis. It's going to be option 1. And so let's go with 16.2 grams of butane. Then what are we gonna do? We're gonna get rid of grams. We're gonna go from grams to moles. So I need the molar mass. And so 4 carbons, that's 4 times 1201. 10 hydrogens, that's 10 times 101. So 4 times 12 is going to be 48.04. And this is just going to be 10, 10. So this is going to be 58.14. So 58.14 grams of butane per mole of butane. The grams of butane cancel. Like, leaves us with moles of butane. Now what we need to do is we need to get rid of moles of butane. So what is the mole ratio here? 2 to 8. So getting rid, we're going to get rid of moles of butane. So there's 2 moles of butane for every 8 moles of CO2. We could simplify that to 4 to 1, but I'll just leave it. And so moles of butane cancel, and we have double the moles because we're dealing with CO2 now. Okay, now I need the molar volume. The molar volume is going to convert moles to liters. And so the molar volume is equal to RT over P. And so R is 0.08206 liters times atmosphere divided by mole times Kelvin. T, temperature is here, is 131 C. So 131 plus 273 would be 404 Kelvin. Divided by P, P is going to be 744 torr, but we don't want torr, we want atmospheres. So an atmosphere is equivalent to 760 torr. Let's make sure the units cancel. Kelvin, torr, atmospheres, and that leaves us with liters per mole. So let's go ahead and do that. 0.08206 times 404 divided by 744 times 760. 33.86. 33.86 liters per mole. Okay, the volume's kind of bigger, you know. Our reference point is about 25 liters. This is kind of big. It's kind of big because the temperature is hot, number one, and the pressure is a little lower, you know, than our standard pressure. But anyway, this is going to be 33.86 liters for every mole of gas. Works for any gas. So moles cancel, and that gives us liters of CO2. Well, so let's go ahead and do the calculation. 16.2 divided by 58.14 times 8 divided by 2 times 33.86, 37.73. 37.73 liters of CO2 is generated. 33.73 liters. All right, let's try out option 2 here. For option 2, we're going to stop short. And so that was 1, this will be 2. We're going to stop here at moles of CO2. So it's basically the same setup. 16.2 grams of butane, C4H10. We're going to go from grams to moles. So mole of butane, C4H10, is equivalent to 58.14 grams of C4H10. Then we'll go to moles of CO2. So 8 moles of CO2 for every 4 moles of butane, C4H10. $16.2 divided by 58.14 times 8 divided by 2 equals 1.114. 1.114 moles of CO2. Okay, then step 2. This is step 1. Step 2, well, 2.1, step 2.2. The next step is to use the ideal gas law. Okay, next, use ideal gas law. Ideal gas law. When we use the ideal gas law, the volume is equal to nRT over P. So N is 1.114 moles. R is 0.08206 liters atmosphere per mole Kelvin. T is T is 404 Kelvin. Divided by P is 744 torr. And then we got to convert torr into atmospheres. Torr cancels, moles cancel, kelvins cancel, atmospheres cancel. It gives us liters. So 1.114 times 0.08206 times 404 divided by 744 times 760. That's 37.74. 37.74 liters. These numbers should come out exactly the same, but you know what I did? They don't come out exactly the same because I rounded this one here. I just used 33.86, whereas this one I just used all the digits of my calculator. Or maybe I made a mistake.
You put 2 moles over there and it's 4. Is that different? Should be the same.
Oh shit! You're right. 2. It should be 2. So maybe that was the reason. Yeah, that could be the reason. Maybe that's too big for round off. Let me recalculate it. 16.2 divided by 58.14 times 8 divided by 2 goes 1.114. I might have written 4, but maybe I was thinking 2 when I did the calculation with 2. It's, well, we have 33.73, that's 33.74. And so that's pretty close. It's just round off error. Although the numbers should be exactly the same because I'm using the same numbers. It's just because I rounded this left calculation prematurely here. I didn't carry all the digits in my calculator. That one I carried all my digits in the calculator. So let's see what they got. They got 37.8. 37.8. Oh, I see. Look at what they did. Here, 58.14, they got 58.12, so different rounding there. And then 33.9 for the molar volume, I got 33.86. So it's off a little bit. That's all right, that's within round off. Okay, the other method is to stop at moles of CO2 and use the ideal gas law. And so we redo the calculation, calculate the moles of CO2, and then plug that into the ideal gas law. Yeah, so they calculate 1.11, I got 1.114, and then they plug it in and they get 37.6, I got 37.7. Is that clear? Yes. We could do another problem here. let's try this one. Let's say, how many liters of oxygen are required to react with 2.38 liters of methane? How many liters of oxygen are required to react with 2.38 liters of methane? Now, the thing is, we have to do this. We have to make an assumption. We're going to assume that both are at the same temperature and pressure. Same temperature and pressure. Because if the methane is at a different temperature and pressure, then the volumes aren't going to be proportional. But if both are at the same temperature and pressure, then it's super easy. How many liters are we going to need? Well, if I have 2.38 liters of methane, then all I do is this. I see that I'm going to need twice as much oxygen. So 2 liters of oxygen for every 1 liter of methane, which is going to give me 4.74 liters. Does that make sense? It's just a straight volume ratio. And so what we're going to do is we're going to add a twist to that. Here. If I had 10 liters of methane, how many liters of oxygen would it require? 10 liters? No, 20 liters. All right, this works only if the temperature and the pressure is the same. And so let's take a look at this active exercise here, in which the temperature and pressure actually are different in gases. And so in this next example, we're going to do is, let's look at sulfur. This is solid sulfur with O2 gas yielding SO2 gas. What kind of reaction is this? This is an element plus element combination or combustion. This is just a combustion. We're burning sulfur. Burning sulfur, you're going to make sulfur dioxide or other oxides of sulfur. So if I have 1.75 liters of O2, then how many liters of SO2 do I have? Well, the liters of SO2, if I have 1.75 liters, I'm going to form 1.75 liters of SO2 if at same T and P. Does that make sense? And so if I burn this, this many moles, I'm going to form that many moles. This is 1-to-1 mole ratio or 1-to-1 volume ratio. And so 1.75 liters of this is going to lead to 1.75 liters of this, as long as the temperature and the pressure are the same. However, they change the temperature and pressure. And so this is going to be at 24 degrees C and 755 torr. But if the temperature is changed here, and so this will be the same. Now, if the temperature changes, what will the volume be? If the temperature changes from 24 degrees C to 165 degrees C. So the temperature goes from 24 degrees C to 165 degrees C. Well, what do you expect to happen? If we are close to room temperature, about 25 liters, if we increase the temperature, what's going to happen to the gas? It's going to grow bigger. It's going to expand. And if the pressure changes, if the pressure goes from 755 torr to 785 torr, yeah, what's going to happen? The gas is going to compress. Not hugely, because this is not a big This is a huge temperature change maybe, but this is not a huge pressure change. So a little bit of compression, maybe a lot of expansion. And so you know what this is? This is perfect for the combined gas law. And so we're looking at SO2. For the SO2, initially it's going to be 1.75 liters. So P1, V1, T1, N1. This is what we need for the combined gas law. And then we're going to switch it to P2, V2, T2, N2. Okay, N, did we add more moles of gas or did we remove moles of gas? Did we, in other words, did we add more gas or remove gas? No. You know, all we're doing is we're taking a 1.75 liter balloon and heating it up and compressing it a little bit, or putting a little bit more pressure on it. And so the moles doesn't change. We didn't add or remove gas. And so this is a constant here. So we'll just get rid of it. In other words, we have this equation, P1 V1 over N1 T1 is equal to P2 V2 over N2 T2. If the moles don't change, then we'll just cancel it because of the same number. All right, P1 is 755 torr. P2 is 785 torr. V1 is 1.75 liters of the SO2, and V2 is, we don't know. T1 is 24 degrees C. 24 degrees C plus 273 would be 297 Kelvin. So this is 297 Kelvin. T2 is 165 degrees C. 165 plus 273 would be 438. 438 Kelvin. And so we're just going to plug it in here. We're going to solve for V2. So V2 is equal to P1 over P2 times T2 over T1 times V1. So the pressure is going to go 755 over 785. The temperature is going to go, T2 would be 438 over 297, and V1 is 1.75 liters. So let's go ahead and calculate that. So 755 divided by 785. So the pressure should shrink it down, times 438 divided by 297. The temperature should expand it, times 1.75. 2.482 liters. 2.482 liters. So that 1.75 liters is going to grow to 2.42 liters. So that's what they got here, 2.48 liters. And the units cancel, you know, as long as the units are the same. Torr cancels torr, Kelvin cancels Kelvin. We could use any pressure unit for this equation. Torr, atmospheres, bar, doesn't matter. But we can only use one temperature unit for this equation. The temperature unit has to be in Kelvin. All the others just have to cancel. That's it. All right, we'll stop here. We're going to take a break.